Hey there, science fans! Today we're diving into the wacky world of acids and bases. These chemical compounds are all around us, playing a vital role in our daily lives. From the food we eat to the soap we use, acids and bases are essential for life as we know it. But what exactly makes a substance acidic or basic? Let's explore the fascinating theories that explain these chemical marvels. Acids and bases are like two sides of the same coin. Acids have a sour taste and they can be corrosive. Think of lemon juice or vinegar. On the other hand, bases have a bitter taste and can feel slippery. Imagine soap or baking soda. Understanding these substances is crucial in fields like medicine, agriculture, and environmental science. So put on your safety goggles and let's unravel the mysteries of acids and bases together. Our journey begins in the late 19th century with a Swedish chemist named Svante Arrhenius. He was the first to propose a widely accepted theory of acids and bases. Arrhenius noticed that when certain substances dissolved in water, they produced electrically charged particles called ions. He defined acids as substances that produce hydrogen ions, H+, when dissolved in water. For example, hydrochloric acid, HCl, found in our stomachs, dissociates in water to form H+ and chloride ions, Cl. This increase in H+ ions is what gives acids their characteristic properties. Arrhenius also proposed that bases produce hydroxide ions, OH, when dissolved in water. Sodium hydroxide, NaOH, commonly known as Li, is a classic example. It dissociates into Na+ and OH ions. The presence of these ions influences how bases react with other substances. Fast forward a few decades and two chemists, Johannes Bronsted and Thomas Lowry, independently expanded upon Arrhenius's theory. They realized that acid-base reactions involve the transfer of protons, H+ ions. According to the Bronsted-Lowry theory, an acid is a proton donor while a base is a proton acceptor. This definition broadens the scope of acids and bases beyond those that simply produce H+ or OH ions in water. For instance, ammonia, NH3, acts as a base by accepting a proton from water, H2O, forming ammonium, NH4+, and hydroxide ions, OH. Water in this case acts as an acid by donating a proton. This concept of conjugate acid-base pairs is central to the Bronsted-Lowry theory. Now let's jump ahead to the 1920s, where American chemist Gilbert Lewis revolutionized our understanding of acids and bases. Lewis focused on the behavior of electrons, the tiny particles that orbit the nucleus of an atom. He proposed that acids are electron pair acceptors, while bases are electron pair donors. This definition goes beyond the limitations of proton transfer and encompasses a wider range of chemical reactions. For example, boron trifluoride, BF3, which lacks a hydrogen atom, acts as a Lewis acid because it can accept an electron pair from a Lewis base, such as ammonia, NH3. This electron pair sharing forms a coordinate covalent bond, expanding the concept of acids and bases to include reactions without proton transfer. Section 5. Comparing the theories: a balancing act. So far we've explored three main theories of acids and bases. Each theory builds upon the previous one, providing a more comprehensive understanding of these fascinating substances. Arrhenius's theory laid the groundwork by focusing on ions in aqueous solutions. Bronsted and Lowry expanded the definition to include proton transfer, while Lewis's theory provided the broadest perspective by emphasizing electron pair interactions. While these theories may seem different, they are interconnected and complementary. Arrhenius acids and bases are also Bronsted-Lowry acids and bases, and Lewis's theory encompasses both. Understanding the nuances of each theory allows chemists to predict and explain a wider range of chemical reactions. Section 6. Real-world examples from vinegar to soap. Now that we've delved into the theories, let's look at some real-world examples of acids and bases in action. Vinegar, a common household ingredient, contains acetic acid. This weak acid is responsible for vinegar's sour taste and its ability to react with baking soda, a base, to produce carbon dioxide gas. Soap, another everyday item, is made by reacting a strong base such as sodium hydroxide with fats or oils. This process, called saponification, creates a molecule with a polar head, which is attracted to water, and a nonpolar tail, which is attracted to grease. This unique structure allows soap to dissolve grease and dirt, making it an effective cleaning agent. Section 7, Acids, Bases, and the pH connection. You've probably heard of pH, a measure of how acidic or basic a solution is. The pH scale ranges from 0 to 14, with 7 being neutral. Solutions with a pH less than 7 are acidic, while those with a pH greater than 7 are basic. The pH of a solution is crucial in many biological and environmental processes. For example, our blood needs to maintain a slightly basic pH of around 7.4. Any significant deviation from this range can disrupt bodily functions and lead to health problems. Similarly, the pH of soil affects the availability of nutrients for plants, influencing agricultural productivity. Section 8. The importance of acid-base chemistry. Understanding acid-base chemistry is essential in various scientific disciplines and everyday life. In medicine, medications often interact with the body's acid-base balance. For instance, antacids neutralize excess stomach acid, providing relief from heartburn. In environmental science, acid rain caused by the release of sulfur dioxide and nitrogen oxides from burning fossil fuels has detrimental effects on ecosystems. Understanding acid-base reactions is crucial for developing strategies to mitigate pollution and protect our environment. Section 9, Conclusion. Keep exploring the chemistry of our world. Acids and bases are fundamental components of the chemical world, influencing countless processes around us. From the tangy taste of citrus fruits to the cleaning power of soap, these substances play a vital role in our daily lives. By understanding the theories of Arrhenius, Bronsted-Lowry, and Lewis, we gain a deeper appreciation for the intricate interactions that govern the behavior of matter. So, the next time you encounter an acid or a base, remember the fascinating chemistry at play. Keep asking questions, exploring, and marveling at the wonders of the chemical world.